All right, so hopefully you guys are weathering this virus well. Um, so today, or this video, is on tension and pulleys, and it's another good example of how to combine Newton's laws together, and and shows how things are quite literally tied together. Um, so anyway, so we're going to do this problem twice. We're going to have a mass sliding along a table, going around a pulley, from which another mass of size little m hangs. And to get started with, I'm going to assume there's no friction at the top. And then we will resolve it with friction. Little things to watch out. The physics of this is not hard. Where people get caught is you have to solve two equations with two unknowns, and unlike in a math class where the instructor will say, "Hey, you have to do this," a physics problem won't tell you that that's what you're going to have to do. So I'm telling you. So when we'll get to a point where it looks like we don't have enough information. Well, that's because we have to use a second equation. Very good. So we're going to have these two objects. I could give you numbers and let you work it out, but because I know that Dylan loves to do algebra, we're going to do everything symbolically and then substitute in. All right. So there's no friction at the start, and then we'll go back and add friction, and it changes things in a more or less predictable way. Okay, so the goal for this problem is to find a formula for the acceleration of the hanging mass, and also find a formula for the tension on the wire. Now, some words about wires and pulleys. In this course, unless explicitly stated, we are to assume that we have magical, mystical unicorn pulleys and wires. And so that means that the wire or rope, it doesn't matter what you call it, has no mass, doesn't elongate or stretch, and our pulleys spin with zero resistance. That simplifies the analysis greatly. So let's get started. We have two objects. We're going to need two free body diagrams because, well, that's just what we have to do. So let's start with the simplest one. So what are the forces acting on the small mass? As you look at it, there's weight pulling it down because we're on Earth, and there's also a tension going up. Occasionally I get students who say there's a normal force, and that's not right. It's not resting on anything. It's not in contact with the surface. The tension is what's pulling up. So the free body diagram would look something like this. We have a weight, and I'm going to be very careful here because we have a big M and a little m. So let's label this as the weight for little m. And then we have a tension force going up. All right. Now, at this stage, many people lose it, and they can't save the problem from there. Many people say that these two forces should add up to zero. But if you think about it, that means that there's no acceleration. But if there's no acceleration, if we require from the beginning that there's no acceleration, and that's not a true thing, that means everything that follows is wrong. So here, we don't know what the acceleration is. The only thing we know about is the weight. So That's the only thing we're allowed to assume at this point. The other free body diagram for the large mass has the following form. There's a tension. Now on the large mass, the tension pulls to the side. And then there is also a normal force and a weight for the large mass. And that's it. We've ignored friction, so there's nothing else in this free body diagram. A comment. Because the pulley has no friction, we assume, then it does not affect the forces, the size of the forces on one side versus the other. It just freely rotates as needed. And I should have also said this, we assume that the pulley and rope system turns without any slipping. So the only effect of a pulley is to redirect and change the angle at which the forces are applied. But the magnitude of the tension is not affected. That's what we assume because the pulley is frictionless and because the wire is massless. All right. Very good. So that means that the tension on the little mass is exactly the same in magnitude as the tension on the large mass. And we will just call that number T. And whether it's to the right or whether it's, an upward force, just look at the picture and you can interpret it in the right way. Okay. So we've got two free body diagrams, and we can write down the net force for the small mass. So let's focus on the small mass object. Then we can write down a formula for the net force. We know that F net in the y direction equals, well, I have tension going up, so it's a positive T, and I have a weight going down, so that's going to be minus little m times g. That's the formula for the net force that I get from the free body diagram. If I set that equal to mass times acceleration, now I should be a little careful here. So I'm going to segment this so we don't get things confused. Okay, so tension minus mg, that's the net force in the y direction on the small mass. That must equal the mass times the acceleration in the y direction for the small mass. Great. Next up, let's focus on the larger mass object. Since I'm solving it symbolically, it doesn't truly have to have a numerically larger mass. I'm just using a capital letter here. Okay. Now, in the y direction, we can write down that force. So for the large mass, capital M, we get the net force in the y direction equals a normal force going up, and then we have a weight going down, minus big M times g. Now, I'm doing that because we will use this later on. In this problem, it turns out we don't need this because there's no friction, is really why we don't need it. There's no motion in the vertical direction. Remember, the Dukes of Hazzard, it's just a movie. It's not real. Cars can't jump. Okay? So this mass can't move in the y direction. It's only allowed to move horizontally. And so that means that the acceleration in the y direction is 0. And we learned that the normal force equals big M times g. So that's a truism. It's just not a very useful quantity to know. More useful is going to be the net force in the x direction. So if I write down F net in the x direction on the large mass object, well, I look at that and I only have one force in the x direction. So that's simply the tension. And that must equal the big mass. Okay, now I have a problem. I wasn't careful enough. Because I have two objects, I, in principle, could have two accelerations. We'll come back to that in a minute. So I should go up here and label this acceleration according to the mass who actually has that one. And I should say this one is in capital M times A with a capital M subscript. All right. So I have, maybe I should box it in so it's easy to see. I have an equation here, which is a good one to know. And I have an equation here, which is good to know. At this point, I like to remind myself where I am and what am I doing, how I got here. So I'm in my kitchen, which is kind of weird. But what I'm doing is trying to find the acceleration of the hanging mass and the tension on the wire. Now I have two equations, but if you're keeping, if you're watching closely from home, you'll see that I have unknowns, T and acceleration, and T and acceleration of the big mass. So I have three unknowns, really, two accelerations and one tension. So how can I proceed? Well, the next step in this process is to realize that if I move the little mass down 1 inch, then the big mass would move over 1 inch. And if I move the mass down 2 inches, the big mass would move over 2 inches. So there's a correlation. The wire correlates the motions of the two masses such that at least the size of the motions are 1-to-1. Now it turns out with the standard conventions, we're going to say that moving down is negative, so the small mass will have a negative displacement, whereas we'll say that the big mass has a positive displacement because it's moving to the right. So ignoring unit vectors, because that doesn't really matter, just focus on the scalar prefactors of things, we see that the acceleration of the big mass is always going to be equal but opposite the acceleration of the small mass. So I can write my last equation that I need as acceleration for the big mass equals minus the acceleration for the small mass. All right, so those are my equations that I needed, because remember I had three unknowns, and now I have figured out a third equation. So now I have three equations and three unknowns. Great. So remember these equations. I'm going to have to erase stuff to make some room, but the key ideas now are going to be that the accelerations are correlated, and then I can just substitute in. So what I'm going to do, since the goal is to find the acceleration of the small mass, I'm going to use this third equation to eliminate the acceleration of the big mass here, and then solve the equations together. All right, so take a second, maybe take a second and write these box-in equations down so that you can know where I'm getting things. Okay. I'm just going to keep my free body diagrams for when we add in friction. All right. Okay. Now, we want to solve for the motion. So my equations are, let's do the equations in blue. That seems to, blue or black seem to show better. The equations are that we have T minus little m times the acceleration of the little mass. Oh, sorry. T minus mg equals the little mass times the acceleration of the little mass. And on the other hand, after I substitute in and eliminate the large mass's acceleration from the equations, I get T equals minus big M times the acceleration of the small mass. This minus sign comes from the correlation between motions. All right, now what we need to do is clear. So I just have two unknowns, the tension and a mass, and I have to solve them. And I can't focus on one equation and ignore the other. You have to solve them simultaneously. Now, there are lots of ways to do this. Probably the easiest way at this point is simply to substitute in for tension the following equation and then rearrange things, watching the minus sign. So when we do that, I substitute in, and I'm going to rearrange, kind of look at it. Well, we can do it. All right. So that's going to be, oh, wrong color. So I substitute in, and I get minus big M times A little m minus little m times G equals little m times A M. And then the strategy is to move this over the equal sign, which it makes it positive. And then I'll have two terms, both with a factor of the acceleration. And so I can regroup. So I'm going to get minus mg equals little m plus big M times A sub m. Rearranging it, I get the following result. I get that the acceleration for the small mass equals minus little m g divided by little m plus big M. Whoa. All right. That's one equation. The other equation then simply comes from substituting this result in up above, and we get that the tension equals, now let's count minus signs. There's one minus sign here, there's another minus sign there. When it comes to minus signs, if you're going to be wrong twice. In this case, we're not wrong at all, and we get big M, little m times G divided by the sum of big M plus little m. All right. So hopefully you followed that. And to be honest, this is algebra worth doing. And there's algebra that doesn't do anything, and then there's algebra that's worth doing because it shows that you have mastery over the concepts. And this is one you should do. Just a comment. If I had not known or noticed this minus sign, it would have, when it feeds through, that would have changed this minus sign, which would have made the plus sign a negative, and we would have known that we had a problem because we would have had a situation where potentially you could get a divide by zero problem, which would be an infinite acceleration, and that type of thing can't happen. So we did this right, and we can check that in a couple ways. Well, one is to make sure that there are no places where it blows up. So good, the world won't end. The other thing is, if you made the large mass massless, or equivalently, if you snip the rope. If you snip the rope, then, and only then, the small mass would be in free fall. If you cut the rope, then the tension goes away and it's in free fall, and the acceleration you should get would be minus g. Well, let's see what happens. If we set the capital M to 0, like cutting the rope, the small mass factors divide out, and you in fact get just the acceleration for the small mass equals minus g. So this is the right answer. This is good. Another good thing is the tension is positive, and so that's good. You can see things like, for example, if the small mass was a mass of 0, then the tension would become 0. So that's one thing. The other thing you can notice is if the large mass became infinite, maybe it was like the wall of the room or something like that. Well, then the mass shouldn't move at all. And look what happens for both formulas. If the capital mass, capital M, is infinite, the acceleration just becomes 0, so nothing moves. And the tension, if you take the limit, or you could use L'Hopital's rule if you wanted, but if you take the limit, you're just going to get that the tension equals mg, the small m times g. So, which is what you would have if you just had a hanging mass. So the formulas are right, and by taking various limits, you can verify that. Okay. I was going to do the friction one here, but this video is getting long, so I'm going to stop this one and then start another video where it's the same problem, but now we're going to add in friction. Okay, hope you guys are healthy and doing well. See you around.